Hello, this is complex analysis for March 11th. Let's get started. So in today's lecture, what I want to do is introduce Riemann Zeta-Function, and it's a famous Riemann Hypothesis problem. There's a $1 million prize on that problem. I think today's lecture is going to be mostly kind of overview of the connection between what we've been doing and how it relates to this problem. I'm not going to prove very much about the claims I'll make. So I'll tell you about what's known, but the justification is a little bit out of scope for us. Although some of the stuff could be done with more time. There's a capstone project in there. So, well, let's get started. So here's the definition of Riemann zeta function. It's an infinite series of 1 over n to some exponent s. So note that s is the variable here, not the n. N is counting from 1 to infinity, and s could be thought of as a complex number, some kind of exponent on n. This is not a power series, so it doesn't have to converge in a circle. In fact, it converges on a certain half plane. So I'll get to that in a second. Riemann zeta function, it's named Riemann zeta function, but really it was first introduced by Leonhard Euler, who used it to study prime numbers. In particular, he showed that 1 over the prime number for all the prime numbers is a divergent series. So that says something. Well, first, it shows that there's infinitely many prime numbers because it diverges. You have to be adding infinitely many things. But also it says something about distribution of primes as well. So if prime numbers are super rare, 1 over prime numbers might converge because prime might get big very quickly. But if it's divergent, that means there are, in some sense, a lot of prime numbers out there. Okay. But Riemann used this function to get results about how the prime numbers are distributed. So we'll get there. Okay. So note that we know one thing about zeta function. So if you think let S be 1, so it's just sum of 1 over n, and that's a harmonic series. So we know that this thing diverges. So it does not converge there. Let me show that it does converge if you take S that's larger than 1. So what I'm going to do is what's called integral test, but imagine a continuous version of this, 1 over x to the s. That's a curve that looks something like this. And note that this curve has area beneath the curve larger than sum of 1 over n to the s for n2 and above. So I'm gonna use that comparison. So this zeta function is less than or equal to the first term. So 1 over 1 to the s is always equal to 1. And then for the rest, I could compare that against the integral of 1 over x to the s, where x goes from 1 to infinity. Okay, we could just use the power rule, right? So we could add 1 to the power and divide by that power. And then we're going to plug in, so I can't plug in infinity, but I can replace that with a variable b, and then plug it in, and then let the limit as b goes to infinity. So this thing is convergent as long as the exponent s minus 1 is positive, right? So the middle term goes to 0. So that's what we get. So this zeta function converges if s is a real number greater than 1. If s is a complex number, we could show that it's absolutely convergent. So what we could do is look at the absolute value, and n to the s is an awkward thing to work with. So what we could do is we could look at it e to the natural log of that thing, right? So e to the log of n to the negative s power. We could use one of the log rules to bring the exponent negative s down to the front of log. Okay. And note that now we're taking log of just positive integers n, right? So the complex log function is just natural log function at that point for real numbers. And we're looking at the modulus of e to the negative s times natural log of n. We know that the modulus of exponential function is given by the real part of the exponent, right? So I rewrite that in the next step. And note that natural log of n, this thing is already real. And negative part is, multiplying by -1, which is a real number. So I could pull that outside of the real part. And I could rewrite it as e to the negative natural log of n times real part of s. Now I can kind of go back and make this negative real part of s into the exponent of n inside, and then rewrite the sum as sum from 1 to infinity of 1 over n to the power of real part of s. Okay. So what I did was I started with the modulus of the zeta function and showed that that was equivalent to looking at the sum of 1 over of n to the real part of s. So really only the real part of s contributes to the modulus of this zeta function. And we know when this converges. We know that this converges when the real part of s is strictly greater than 1. We know it blows up at exactly 1. Okay. All right. So let's look at Riemann's contribution to this zeta function. So it turns out that this is an analytic function. So we know that the zeta function is defined for real part greater than 1. So that's the shaded region to the right there. But you could actually do analytic continuation and define it for pretty much all of complex number, all of the complex plane, except for when s is exactly equal to 1. There's a pole there. Okay, so this function could be extended to other parts. One interesting note is that when s is exactly equal to -1, we can rewrite this the zeta function as 1 over n to the -1, which is just adding up n. And we're you could kind of look at that as the sum of 1 plus 2 plus 3 plus 4 plus and so on. Clearly, this is a divergent series, so it's kind of nonsense as I wrote it. But if you talk about analytic continuation, you can kind of imagine, well, you could actually extend that function and make sense of it. As long as you avoid that pole, you can make sense of it. So there's, I don't know if you've seen it or not, but there's a viral number file video that claims that 1 plus 2 plus 3 plus 4 and so on is equal to negative 112. This video is absolutely nonsense. It claims a lot of weird things. It's done by physicists, and they make a lot of incorrect claims. Let's just say that. But you could make a mathematical rigorous argument. And in this analytic continuation sense, the value of the function there is negative 1 over 12. So you could make sense of this. And the reason why they're talking about it is because this zeta function does appear in a lot of physics literature. So it is used in physics as well. I just wanted to mention that because now you can understand the real reason why this is equal to negative 1 over 12, and not just the bullshit reason that's given in the video. Okay, so it turns out that the zeros of these functions have a significant meaning as far as how the prime numbers are distributed. So let's talk about the zeros. It turns out that there are some zeros that are easy to understand, and there's some zeros that's harder to understand. As long as you're looking outside of what's called the critical strip, that's the strip when the real part is between 0 and 1. So we're talking about this portion is what's called the critical strip. Okay. If you're looking at the zeros outside of that critical strip, it turns out that there are zeros on negative even integers. So that's just a fact about zeta functions. And I don't know how trivial it is, but they are called the trivial zeros of the zeta functions. What's interesting is the zeros within the critical strip. Okay, and this is where the Riemann hypothesis comes in. So in that critical strip, all of the zeros of the zeta function lie exactly on the line real part of z is equal to 1/2. So this center vertical line on the critical strip contains all of the zeros on there. That's the Riemann hypothesis. So we don't know this for true, but if you can prove it or disprove it, you will be owed $1 million. Okay, so there's been a lot of research on this topic. So we know that there are infinitely many zeros on that strip. We kind of know the asymptotic distribution, how much zeros are there. That's known. Somebody proved that at least 1/3 of the zeros line on the critical line, real part of z is 1/2. Now I know that doesn't make any sense as stated, because 1/3 of infinity is really infinity. But you could make sense of this argument. We can use computers to compute trillions and trillions of zeros. And so far, all of them lie on the critical line. So it's looking like it's probably true, but that's evidence is not a proof. And I mentioned this already, but Riemann hypothesis is a list of 7 Millennium Prize problems. So there's 7 mathematics problems that was offered in the year 2000, each of them worth $1 million to solve. Only one is solved so far. That's the Poincaré conjecture, solved by Grigory Perelman. He's a Russian mathematician. So Riemann hypothesis is still open. It's worth $1 million. Okay. And the reason why people care about it is because of its strong connection with prime numbers. Right? So let's talk about prime number theorem next. Okay. So before I talk about prime number theorem, I need to define a new function, pi of x. I know they use the letter pi, but that makes sense in this case because pi is a Greek p, right? So p for prime. Let's say pi of x is the number of primes less than or equal to that number x. And pi is called the prime counting function. So 1 is usually not considered a prime, so pi of 1 is equal to 0. 2 is the smallest prime, so pi of 2 is 1. 3 is also a prime, so pi of 3 is 2. 4 is not a prime because 4 is 2 times 2. So the prime counting function does not increase at pi equals 4. 5 is a prime. 6 is not a prime. 7 is a prime. So pi of 7 is equal to 4, but you won't get another prime until 11. So pi equals 7 through pi of 10, they're all equal to 4. Pi of 11 is 5, and so on. I hope that makes sense. All right, so here's the prime number theorem. So this is actually a theorem. We have a proof for it. Although I can't cover it in this course. The prime counting function is asymptotically equal to x divided by natural log of x as x goes to infinity. So this squiggly symbol means asymptotic. The definition of that is really if you take a ratio of this, the limit is equal to 1. So you could take this as another statement, more precise statement for the prime number theorem. So pi of x divided by x over natural log of x goes to 1. That's the prime number theorem. Okay. So, as mentioned before, Euler did some arguments with zeta function about distribution of prime numbers long ago. 60 years later, Legendre and Gauss conjectured that prime number theorem should be true based on a whole bunch of calculations that them and their assistants did. In 1859, Riemann published on the number of primes less than a given magnitude. This is a very famous paper that's been cited many, many times. He extended the zeta function to all of the complex plane except for s equals to 1, and introduced these revolutionary ideas that people are still trying to understand. Okay. And Hadamard and de la Vallée-Poussin used these ideas to prove prime number theorems about 30 or 40 years later. Okay. So far it's unclear why zeta function has anything to do with prime numbers. So let me just give you a taste of what Euler did. So here's how he argued. Okay, so we have the zeta function. This is the sum of 1 over n to the s. Ignore the s for now. That's the sum of 1 over all of the positive integers. We know that each positive integer is a unique combination of some powers of prime numbers. So another way to say that is that it's a product of the sums of different powers of primes. So for example, 1 plus 1 over 2 to the s plus 1 over 4 to the s. So this factor is all of the powers of 2. And the next factor is all of the powers of 3. And the next factor is all of the powers of 5, and so on. So you have a factor for each prime number, and you list out all of the powers of that prime. And each number, like 1 over 12 to the s, could be written as some combinations of powers of prime. So 12 could be written as 4 times 3. So it's powers of 2, 2 squared times 3. So these two combinations will make up 1 over 12 to the s, and I guess 1 from the rest of the factors. So if you multiply this out, all of the positive integers could be written out that way. Okay. So it's a product of all the primes p of sum of all of the powers of that prime. Okay. But you could actually look at this sum. This is a geometric series. You could, with the exponent k, you could take that out, and now this part is a geometric series. So we can actually compute that, right? It's 1 over 1 minus the ratio. So we started with this zeta function right here, and we've written in a different way. So it's a infinite product of factors that look like 1 over 1 minus 1 over p to the s. I don't know if this is any easier to analyze, but you can see why prime numbers plays a role here. Okay, so it turns out that it can be shown that this product shows that the zeta function is never equal to 0 for s, real part of s greater than 1. So the right side of the critical strip has no zeros. Okay. It turns out that the key step in the proof of prime number theorem is showing that there's no zeros on the line where the real part of s equals to 1. So that's on the border of the critical strip. So this is the critical strip, and you show that there's no zero on this line, and it turns out that that's equivalent in some sense to the proof of the prime number theorem. So showing that 0 doesn't exist there is already saying something about distribution of prime numbers. Okay, and in fact, the proof shows something, how the prime numbers are distributed. So prime counting function is equal to some integral, the integral being 1 over log of t from t equals to 2 to x, plus some error term. Okay. And Bangkok gave this possible bounds on the error terms that's written here. assuming Riemann hypothesis. So if you can write down all of the zeros, and if they lie on the critical line, then we actually know how the error terms behave. But for that, we need Riemann hypothesis to be true. Yeah, so let's see, I think that's all I wrote down. Okay, that's all for today. This will conclude all the lecture part of this course. I will still be posting some review material for complex analysis in preparation for the final exam. But I just wanted to say I really enjoyed teaching this course, and I wanted to show my excitement and how I think this subject is beautiful, and I hope that came through through the lectures. Right? Stay healthy, and I'll see you guys later.